Hello all. In our previous couple of lectures, we have seen some of the applications of sequential design, and the most important one, the one which we have studied in last couple of lectures, were a sequence detector. So, for designing a sequence detector, the approach used to be that we were first designing a state machine, and then state machine or a state graph, and then state table, and then implementing it using it. But there could be other interesting applications also. So we will pick up the old topic which we have already done, arithmetic design. We have already learned how to do addition, multiplication, and various kind of adders and multipliers we have seen. So in this lecture as well as the next lecture, we'll focus again on these arithmetic units now from the sequential design perspective. When we are looking these designs from the sequential perspective, so we will try to see that what kind of benefit can be there if these designs, this adder, multiplication, or any arithmetic circuit for that matter, if they are designed using sequential circuits, then what kind of advantages we can get. And one more important point to note here, that whatever techniques we are learning in these two lectures are generally applicable for any kind of a design. Combinational design can be converted into sequential design using these techniques. So the objective, let's say the first objective is we would like to design an adder which the addition is done over multiple cycles. Okay, why would we like to do that addition in multiple cycles? So you have seen that one clock cycle depends on the latency of my adder. So if latency of that adder is large, then we will not be able to, if latency of that adder is large, then the clock period will also be large. So the solution to that could be that if we do the same addition over multiple cycles, then we can reduce the clock period. So that's the overall objective. So let's try to do it in a very simplistic manner. And the first objective is we would like to design any n-bit adder using one full bit adder. So if we want to do one full bit adder, one n-bit adder using one full bit adder, so the inputs are, of course, you have n-bit numbers, 2 n-bit numbers, and output is 1 n-bit number. Additionally, carry Cout is also an output. So let's, to make the problem even more simple. So what we are trying to do is we are trying to design an accumulator where the output is also saved in one of the operands. So let's say two operands are A and B, and the result is also stored in the A. So when we are saying A and B are two operands, so both of them are n-bit numbers, and result is also an n-bit which is saved in A. So since we would like to design n-bit addition and on the other hand we are also saying that we have to do this addition only using one full bit adder. So one full bit adder will be adding only 3 bits at one time, one bit from A, another bit from B, and one carry in, and will be producing only one bit of sum at one point of time. So we need to store, and we are saying that this addition would spread over multiple cycles. So that means we have to store these numbers A, B somewhere. So these n-bit numbers has to be stored. Where shall we store that numbers? So since we have already studied registers and flip-flops, so what we can do is we can use n flip-flops and create a register, and we store them in a register. Okay, so the other question which comes to our mind, that yes, we can store these A and B in registers. The other question is that now the adder is a single bit, and we would like to add these n-bit numbers. So most likely the thing which is coming to our mind is that we would probably add bit by bit. So we can probably add bit number 0, then bit number 1, then bit number 2, then bit number 3, so on and so forth. So that means all these bits would be probably multiplexed to to our full adder. So each input of the full adder then would be multiplexed, and they have to done sequentially, because addition of second bit depends on addition of first bit, and addition of first bit depends on addition of zeroth bit, because there is a carry chain which is going on. So because of that dependency, you cannot do all those things in any order. So it would be in a certain order, that first bit 0, then bit 1, then bit 2, and then nth bit, n minus 1th bit. So and all of these bits has to be supplied to our adder, single bit adder. So what should we do? So one option which comes to our mind is possibly we have to use some sort of a multiplexer, which would keep on choosing that which particular bit to be selected at any particular point of time. Now there is one more idea. You see that because the order of bits is certain, where this one bit full adder is going to first add bit number 0, then only it can add bit number 1, then bit number 2. So can we use shift registers? So the shift register will give us a certain advantage, that at one point of time only one bit would be added, and then if it is 0th bit, then after that first bit will come automatically, then second bit will come automatically after every clock cycle, or when the bits are shifted. So we'll try to use shift registers, and if this whole picture is in our mind, because we are talking without visually looking at it, so let's try to see that how that accumulator, I am calling it accumulator rather than adder, because we are saving the output again in the same register. So let me consider that this probably looks like the basic starting point of the design, that I have these two registers. So to make the problem simple, right now I have taken n equal to 4. So it's a 4-bit adder, but this n could be generic. So this whatever we are learning here, it could be applicable to any n. So you see that this A and B are 4-bit registers, actually 4-bit shift registers. So my full adder is connected to least significant bit of both the registers. So essentially it is, you can also say this is serial in, serial out register, which is shifting always in the right direction. This is serial in, serial out register. So basically the out part is always LSB, and this is the serial in part. So that's the shift register thing. So now these 3 bits would be added. This is bit 1, operand 1, operand 2, and C in would be added, and the output would be sum and carry. Now where should we store this sum? That's also a question, because we were saying that this sum will actually replace this operand 1. Operand 1 is A in this case. So this sum has to replace operand 1, and otherwise we have to use a new register here. Okay, and then we have to replace that register. So and also this is one problem, that this sum, where to be stored, storing this sum. The second thing is that when we would be adding the second bit, let's say A1 and B1, then whatever is the carry out, that should be rippled to the carry in of the next bit. So what we can do is, we can have a flop here, and we can have a flop here, D flip flop, and every clock cycle this C out will become C in. So in the first cycle, the C in could be 0, or we can have a D flip flop which is reset. Reset means reset to 0, so that means C in would be 0, but from the next cycle onwards, the C out would be fed in, and so this will become C in. So for example, when we will see that when the bits would be shifted, then the C out will become C in. And also we are connecting this sum to the serial in, to the most significant bit. So why that would be helpful? You will see that by end of the computation, it would be able to replace this whole A register, and will have the sum as a sum of the 4 bits. Okay, so so far so good. So we are able to this is the minimalistic design, and where we can it looks like that we would be able to add. So let's try to see in the execution cycles that how it would be happening. So now one more feedback path would even more be helpful, that let's say this B is also feedback to this like this is also a serial in serial out register. B is also a serial in serial out register. So what would be the benefit? By end, when the computation is finished, then we would be able to receive. So this B0, otherwise if it is given here and we are shifting it, then B0 would be discarded. If B0 is discarded, then it may be required in later point of time also. So the better idea would be that let's save it, and let us save it in the same register by giving it as a shift rotation. Okay, so in cycle 0 at time 0, this would be the configuration where A0 and B0 would be adding A0, B0 and C in. So at time 0, C in would be the reset value of D flip flop, and then we would be computing sum and C out. So at the end of T0, and when the next active edge of the clock cycle will come, so this sum would be given as an input to this shift register, and B0 would be given as an input to this shift register, and C out would be given as an input to D flip flop. So what would happen at time 1, basically after the active edge of the clock cycle? So S0 will come here, the first sum bit, which was the addition of sum, and A3 would move to this bit, and A2 would move to this, and least significant bit will become A1 and B1. So similarly, because of this parallel in serial out, so basically B0 came to become the most significant bit. Now during this time period T1, A1 and B1 would be added, and C in is actually whatever was the C out generated during the first 0th clock cycle. So then after, by the end of this clock cycle, we will have S0 shifted to right, S1 would be the most significant bit, and similarly B1 will become the most significant bit, and so A2 and B2 would be the least significant bits. C out and C in would behave in the same way. So similarly after T3 and T4, so after T4 you will have all the 4 bits here as the sum. There is no A, because A, the overall design was A equal to A plus B. So now this become the new A, and we have again received B as it was the original point. So at time equal to T4, so you have to notice that this T4 is the beginning of T4. So we have done computation in T0, T1, T2 and T3, and by the end of T3 or in the beginning of T4, we have this sum which is completely ready, and our register B, or the other second operand, is again in the original position where we started. So this way, using a single full adder, we would be able to design any n-bit adder in n number of cycles. And the additional cost you see is having this register. So 2 registers, 1 flip flop, and this way you will see these registers are anyway would be required whenever we are doing addition or multiplication or any other operation, because we would be doing everything within a clock period, and we would be saving the operands in some registers. Okay, so that means this essentially is not an additional cost. Only one D flip flop and one full adder is able to design a complete 32-bit or any n-bit adder, which is quite a significant thing. So we are able to reduce the area to a very minimal number by using this kind of a sequential, we call this kind of a adder as a serial adder. Accumulator is not important because we can have another register as a sum here, which could be shifted always in the right direction, and by the end of n cycles we can have sum as another register. So we did accumulation for simplification here, but we could have sum as a different register also, so that was not a constraint at all here. So you can see the overall benefit. Area has reduced to a significant amount, but the latency has increased. The overall latency of this design is the latency of one full adder plus the latency of my D flip-flop, and latency of D flip-flop would also involve setup time of D flip-flop. So that means this would can increase the clock period to a very significant amount. Now so yeah, this is a very generic design, and result would be always available at the nth cycle. Now let us see that yeah, so one more point here, that what if we would like to have a new operand here, new operand in A or B. So that means these registers are not only serial in, serial out, but they also should be universal registers, so that they could be parallelly fed. So at that time, whenever you want to add a new number, instead of B there is a C, so that C could be parallelly given as an input to this register, and similarly some other register A, B, C could be given as a register as an input to this register. So all the four values could be changed at the same time, and then after that we can start. Now this this looks like the the way we have discussed it was mostly the combinational part, or specifically we call it a data path part, where we are doing the data computation. But since it's a sequential design, it depends on multiple cycles. My whole design or my whole calculation is done in n number of cycles. What would be the control steps, or what would be the finite state machine for this particular design? So let's look at the finite state machine. So initially, so for finite state machine, first of all, let's very clearly specify what are my inputs and outputs. My input is, let's say, ST start, and my output is SH shift. So this is the input and output of a control system, the controlling part, or this is the input and output for my FSM, finite state machine. Now let's have a little more specification of the input output also. So when start is 0, nothing should happen. When start is 1, then it would kick in the addition, and after first cycle of start, it doesn't matter what is the value of start, because then addition has started, it would only finish when n cycles has elapsed. And shift would mean that when this A and B registers to be shifted, when they are not to be shifted. So let us start with the reset state S0. In the reset state, my flip flop, which flip flop? The flip flop which was saving my C out or carry, that should be given as a reset. And along with that, I would be always waiting for a start. So if start is 0, then it would still remain in this state. And 0 here, 0 as output means that shift is 0. So that means no shifting would happen if there is no start. So that means my A and B, whatever operands are there in the register, they will remain there. They won't be shifted. Now, as soon as start would be 1, then I would shift and will go to a next state S1. And then after that, after every clock cycle, it doesn't matter whether what is the value of my start, whether it is 0 or 1, I will be always giving SH, or basically shift, as 1. So that would keep on happening till my n-1 cycle, so that my result is almost there. So after n-1 cycle, so that means I have rotated it. So this is the So after n-1 states, we have computed the n-1 bits. So here bit number 0 was calculated, here bit number 1 was calculated, here bit number 2 was calculated, here bit number n-1 was calculated. 0, n-2. So that means one more bit need to be calculated. So that means this is my bit n-1, or the last bit where it would be computed. So here I would say that this is the last step. Okay, so where all the computation has been done, 0 to n-1, all the bits has been computed. So what should be done here? here one thing is sure, that when I reach this state S end or the last state, then there should not be any shifting, unless even if there is this the start is 1. So even if start is 1, there is no shifting which is happening. Okay, so you see that we started here in my S0 or initial reset state when start was 0. Then after that start was 1, then we started. After that start was, we don't care whether it is 0 or 1, but somehow if it is 1 here and we reach this S0 state, that means we will automatically will go to S1 state and all others. So that's why we are saying that if start is 1 and we have finished the computation, then we'll keep on remain in this particular state. Okay, our start is 0, then we will go to the reset state and we will say that we are still we are not shifting anywhere. So one more important thing to notice here, the state machine is written in a slightly different format. So far what we were doing, whenever we were writing the state machine, we were writing here 0 or 1, 0 or 1. Now instead of 0 or 1, we are writing the variable name directly. What is that and why it is so? So this is again a more visually correct way or visually different way of representing the state machine, where we need not to bother that whether it is 0 or 1. We focus on the variable name, and by focusing on variable name, it helps us to recognize that whether we are doing shifting, for example, here, or not shifting. So but we have to also associate that whenever we are saying sh, then it means shift, and whenever we are saying sh dash, that means no shifting. So this way, this is another way of representing a state machine, where instead of writing 0 and 1, we directly write the variable names. Okay, so don't get surprised when we get such kind of a state machine representation, where instead of 0 and 1, instead of direct binary values, we are writing the variable name. So writing variable name has another advantage when number of input and number of outputs are a little more than 1. Okay, so another thing, that if I would like to implement this state machine, then you will see that we can implement this easily using an n-bit modulo n counter. So because modulo n plus 1 counter actually, so this particular state machine can be implemented using modulo n plus 1 counter. So from 0 to 1 we are always shifting. So because we are always shifting, so we can implement this part using a counter. Okay, so this is the addition circuit using a single bit.